Hi everyone, I'm Juliette Millet, and I'm going to present to you an article I wrote with Johan Dunbar entitled The Perceptimatic English Benchmark for Speech Perception Models. In this article, we point out that there is no accurate computational models of human speech perception, and we do not know if the models we have access to, whether it's speech recognition models or others, behave like humans. In this article, we wanted to accurately and precisely compare humans and models on a low-level perception task in order to see what kind of models have a representational space that is the closest to human perceptual space. For that, we use an ABX task and we present Perceptimatic dataset/benchmark that is made of stimuli and human response for those ABX tasks. We present a method to use this dataset in order to compare models and humans. So you probably already know what is an ABX test, but I will remind it to you. So it's a really simple task. We ask the participants to hear 3 sounds in a row. So for example, pap, peep, and peep. And then we ask him or her which sound between the first two is the closest to the last sound. So here the right answer would be B. And for the rest of the presentation, I will call the right answer target and the wrong answer other. The answer of the participant is going to inform us on his or her ability to perceive the contrast ER, to discriminate those two sounds. And we're going to obtain a binary response for each triplet. So if, for example, the triplet is pap, peep, peep. This task is really useful because it's easily transferable to model. Indeed, model can extract from the stimuli that the participants heard representations. And thanks to those representations, we can compute distances. So instead of asking the model which sound between the first two you heard is the closest to the last sound, we're going to compute distances. Distances between other and X, and distances between target and X. We're going to compute the difference between those distances that we're going to call the delta value. And this delta value informs us in the same way than the human response earlier on the ability of the model to discriminate or to perceive the contrast AE. If the delta is really big, it means it can discriminate those sounds really easily. If it's small or even negative, it can't discriminate those two sounds. So our goal is to compare those delta value with the human responses in order to compare model representational space and human perceptual space. So now we know what we want to do. We need stimuli. What we wanted here was to test people not only on sounds from their own language, but also on sound from other language in order to have foreign speech perception informations for models and humans. We wanted to perform the ABX task with really simple stimuli, so we chose triphones like the peep and pap from earlier, or apa, ata, etc. We wanted uncontrolled stimuli for different reasons. The first one being that it has not been done previously with humans, and also because it enables us to test models on the same kind of data that they are trained on. So we used the Zero Resource Speech Challenge 2017 test set that is taken from French and English amateur audiobooks. So the triphones are taken from running speech. We realign and clean the triphones, and we obtain a lot of stimuli, so triplets, that enable us to test more than 200 contrasts in French and in English. Now we have the stimuli, we need to test people. So what we did is that we developed an online experiment and we recruited English-speaking participants on MTurk so they could perform these online experiments. We tested more than 90 English-speaking participants, and it enabled us to test each contrast more than 36 times. Okay. Now we have stimuli, human responses for the stimuli. We need to extract representation from models and compute distances in order to obtain delta values. We use different models. We tested different models in order to illustrate a different kind of theories, and I'm going to detail each of them. The first model we use is just our baseline, and it isn't actually a model. It is neutral acoustic figures that are called Millet-Federbank's perceptual coefficients. So it's our baseline. The second model we use is doing short-term acoustic discovery in an unsupervised way. So it's called a directly processed Gaussian mixture model. And what it does is that it's going to take neutral acoustic filters, each frame of those filters, and it's going to try to organize Gaussians on top of them in order to maximize the likelihood of the model. And it's going to be able also to fit the number of Gaussian it's able to use. What we're going to use as a representation from this model is called a post-diagram. So it's a sequence of vectors. Each vector represents the time frame from the original acoustic features, and each vector is a probability vector, and it represents the probability of this time frame to belong to each Gaussian. So here, for example, for the X1, we see that there's a high probability that this time frame belongs to the red Gaussian, and a low probability that it belongs to the blue or the yellow Gaussian. Another model we use does short-term acoustic modeling, but in a supervised way. We give him the kind of short-term acoustic term that he's supposed to discover in a supervised way. So what we use a bottleneck model. So it takes acoustic features. It's going to have a lower dimensional representation of those acoustic features, and then it's going to augment the dimension of this representation in order to do a classification between different terms that we imposed it. We're going to use different settings. In the first one, the model is trained only on English and is supposed to classify phoneme states. The second one is also trained on English and is supposed to classify triphones. And the third one is trained on 17 languages and is supposed to classify phone states in all those languages. The representation we use for this model is the lowest dimension layer. And then we also use a model that does articulatory reconstruction. So what it does is that it takes neutral acoustic features and is trying to reconstruct articulators' positions in 2D. So it's trained on MR recordings in English. And of course, the representation we use is the articulatory reconstruction itself. The last model we use is an ISR model, a really classical one, developed by Mozilla. It's trained on a lot of English data, and it's trained to do written retranscription from it. So it takes MFCCs, neutral acoustic features, and directly outputs written retranscriptions. It's not state-of-the-art at all, but it's pretty efficient, however. So we don't directly use the letters, the outputs. We used not the last layer, but the one before, because it obtained really good results in terms of ABX error. Okay, so now we have all the representations we need, and we have the delta values from those representations for the stimuli we extracted at the beginning. So we can try to see the link, to study the link between the delta values for those different models and the human answers we obtain. So to make the link between the two, we're going to fit a probit models that takes as input, of course, the delta values and different parameters that are going to influence the humans when they're doing the ABX task. What we're going to do is that we're going to fit for each model a probit model, and we're going to see what kind of log likelihood it obtains once it's fitted. Of course, we're not going to do it once. We're going to resample all the triplets in order to obtain a confidence interval for those like log likelihood. And here are the results we obtain. So what you can see on the y-axis is the log likelihood obtained, average on all the resampling. On the x-axis, you have the different models we tested. If there is a bracket like this one, it means that the difference of log likelihood between the models is not significant. If there isn't one, it means that it's significant. So what we can see first is that the models that are doing short-term acoustic modeling, whether it's unsupervised like those three, the bottleneck models, or this one that is doing it in an unsupervised way, those models are doing pretty well at predicting human results. So their representational space is quite close to the human's perceptual space, or at least they're doing better than the neutral acoustic figures. Another thing we can notice is that the articulation model is not doing really well at predicting human results, and it's probably because the model itself does not really well at predicting articulatory trajectories, because it's only trained on 5 hours of data, which is probably not enough to perform well for this task. The most surprising result we obtain here is the fact that the ASR model is not doing well at predicting human results. And we know that this model is doing pretty well at doing written retranscription. And so it's probably because it organizes its representational space in a different way than humans, than the human perceptual space, and we can see it here. So what we have here is the delta value from the ASR model versus the human accuracy. So the axes are renormalized, so they are comparable. So you have got, for each point, you have a contrast. The white circles are the English contrast, and the black triangles are the French contrast. And what you can see is that there is a correlation for the French contrast, but for the English, which is supposed to be the native language of the humans that are tested and the models, because it's trained on English only, there is no correlation. The model is going to be really good for some contrasts for which the humans are pretty bad, and it's going to be quite bad at some contrasts for which the humans are quite good. So it's organizing its space totally differently. Okay, so as a conclusion, we presented Perceptimatic, which is a dataset made of stimuli and human responses for a low-level perception task, an ABX task. We used it with our methods that we presented to compare at the stimuli level models and humans, which is more precise than any other methods that have been developed earlier. With this method and this dataset, we showed that an efficient ASR model like DeepSpeech does not necessarily predict humans' behavior well. And actually, it organizes its representational space in a different way than humans' perceptual space. Thank you for your attention, and feel free to ask any question you want.